大家好，我是濵口宏夫，金多多指教，今天很高兴能教拉曼公布学。我学了45年拉曼公布学，我不会无聊。拉曼公布是永远性。我不太会中文，对不起，所以我要说英文 ，okay? So I'm now speaking English. I'm sorry for speaking English, but my Chinese is not good enough to give you all the lectures in Chinese. So in this lecture, I'm talking to you about Raman spectroscopy and Raman computer. Okay? And as I said, I have been doing Raman spectroscopy for many, many years. And I was always interested in something new coming out from Raman spectroscopy. And so I hope that you get used to, or just Raman spectroscopy after this lecture, and hopefully you can use it in your own research. The first slide I'm showing you is this one. And this is a Japanese tennis player, Kei Nishikori. Maybe some of you know him. And I like to play tennis very much. And what I'm going to tell you here is that seeing is very important. And you get most of the information you need from your eyes by seeing things. So seeing is very, very important. So you say the Chinese words here, Yim Liao Lian or something like that, then seeing is believing. Okay? So seeing is very important. But if you want to see, you need eyes. Okay? So unfortunately, if you have no eyes, your world is very, very limited. Without seeing the outside world, your life would be very, very much limited. But if you have eyes, more eyes, I should say, then you can see different world. So this is what I'm saying. If you have the eyes of science, or chemical eyes or something like that, I say, then you can see the world in a different way. So doing spectroscopy is something like that. You are seeing the world of molecule by spectroscopy, which you cannot do with your naked eyes. So by learning spectroscopy, you get new eyes to look into the world of molecules. And because you are all chemists, you are interested in molecules, and then it's very important to see molecules by spectroscopy. That's the reason why spectroscopy is so important in chemistry. So here I show you some insects, beetles in Taiwan. So I collect beetles as my hobby. So many times I go into the mountains in Taiwan and collect those beetles. Why they are attractive? Because the shapes, morphology, and color, and also its movement are really interesting. So I like those, especially the stag beetles. I like this one. This one has got a very strange shape. And these very big horns are just for fighting with other stag beetles. Okay? And so when I was a child, I was really fascinated with these stag beetles and other beetles. But here we are using our own naked eyes to see the morphology, color, and movement. So you are using your own eyes to look at or seeing nature. Okay, this is what we usually do. So I just show you an additional one. This is not actually directly related with chemistry. So this is how we collect beetles. We go into the deep mountains and light on this kind of very bright light. And then insects are induced to the light. And then we catch. So there are so many different things. And you know how variety of different things are there in the nature. But then you collect many beetles. And this is a specimen I made already after coming to Taiwan. So there are different morphologies, different colors. That all you do by your naked eyes. But Raman spectroscopy is doing it a little different from this. And it uses lasers. So laser is an abbreviation of the term light amplification by stimulated emission of radiation. And by using stimulated emission, laser can produce a very strong light that is suitable for looking into the world of molecule by spectroscopy. Especially in Raman spectroscopy, we always use lasers. So the invention of the laser benefited Raman spectroscopy very, very much. So owing to the development of laser, Raman can do many, many things now, you know. So laser is very important for Raman spectroscopy. And here I show you two very typical lasers. One is argon ion laser that emits the light at 488.0 nanometer. That's blue-green light. And here you have the helium neon laser that emits the light at 632.8 nanometer. That's a red light. And these lasers you often see in the chemistry laboratory doing Raman spectroscopy. So using lasers, we get some new eyes, which I call chemical eyes. And this is Raman. And this is a picture of Raman, actually. So seeing nature by chemical eyes by using Raman spectroscopy. And Raman is a name of an Indian scientist who discovered what is called Raman scattering in the year 1928. So many years ago, nearly 90 years ago. And it is interesting that Raman got a Nobel Prize in 1930. So only 2 years after his discovery of the scattering. So that means that was a great discovery at that time. So it's very, very unusual that you get a Nobel Prize only after 2 years of the report. Okay, I think this is only example of that short time. So that means also that the discovery was actually really appreciated fully by the scientists at that time. So they all know what they are having by Raman scattering. And by using Raman scattering, you can see molecules. And as I said, if you use laser, you can do it much, much better previously. So Raman scattering, the discovery of Raman scattering was the starting point of Raman spectroscopy. That was 1928. And Raman spectroscopy means spectroscopy using Raman scattering. And here, is there any pointer? No. so I can point. So here you have a spectrum. Spectrum means, say you have a grating a prism and spectrometer, and you have some light. Then you disperse it in different wavelengths and just display like that. So in this particular case, we are shining laser into carbon tetrachloride, CCl4. And then this strong line comes from the laser itself. So there is no change of the wavelength or the frequency for this line, which is called Rayleigh scattering. But in addition to that very strong Rayleigh scattering, you have Raman scattering, for which the wavelengths are different, are shifted from the original one. Okay? So there are two groups of Raman scattering, which is called Stokes-Raman scattering and anti-Stokes-Raman scattering. And in the Stokes-Raman scattering, it appears in the longer wavelengths, shifted from the original wavelengths. And anti-Stokes-Raman scattering appears in a shorter wavelength region than the original wavelengths. And longer wavelengths means lower energy, okay? Lower frequency and lower energy. So that means the photon coming into the sample collides with the molecule and lose some energy and convert it to a photon with lower frequency or lower energy or longer wavelength, okay? Then the difference of energy between the original energy and the scattered photon energy is given to the molecule. So the molecules are excited by the scattering, okay? So this is a kind of inelastic scattering. In elastic scattering, there is a exchange of energy between incident photon and the molecule, okay? So Raman scattering is an inelastic scattering of photon by molecules, okay? So if you measure the energy difference between the original energy at the Rayleigh scattering and the Raman shifted scattering energy, then the energy difference is given to the molecule. That means the molecule can receive that energy. So the energy here, energy difference, reflects the energy levels in the molecule. Of course, in quantum mechanics, we have the discrete energy, and the energy is only given with exactly the same energy, that energy level that the molecule has. So transition from one state to the other, okay? So the reason why we have these discrete lines is that the molecules have discrete energy levels. So in this case, these energy levels are from the vibrations of the molecules that I am showing just after this. So Raman spectroscopy mostly looks at a vibrational spectrum. And if you just say Raman spectroscopy, it means vibrational Raman spectroscopy. Here I show you two interesting sentences. And spectra are letters from the molecule. 公布式分子即来的信. And Raman spectra are molecular fingerprints. Raman 公布式分子的日文, that's not easy for me. And these two phrases attracted me very much when I was a student. And that was the reason why I came into the research of spectroscopy. It's very romantic, you know. Nowadays, you never write letters. You just send mails. But, you know, when I was a student, well, we are still using letters, you know, to communicate with others. So letters, spectra letters from the molecule means that the molecules do send letters to us in the form of spectrum. And if we can read it properly, then we understand what the molecule wants to say us. So a message from the molecule we can receive. But you need to to have be able to read the letter. So reading letters from the molecule is what we learn in spectroscopy, how to read it. And also, Raman spectra are molecular fingerprints. So you have the molecular fingerprint, and it can identify molecule quite easily. So if you have your fingerprint pattern, then you can identify the individuals of molecule, people. But the same holds to molecules. So if you look at Raman spectra, you can immediately know what molecules you are looking at. So it is said that Raman spectra are molecular fingerprints. Okay? And then I have to add one thing. This is Professor Takehiko Shimanouchi, my thesis supervisor. And I liked him very much. Although I never followed his suggestions, but I liked him. And it is very important for you to like your supervisors. You know, if you like your supervisors will like you, and there are very good communications between your supervisor and yourself. That makes your scientific discussion much, much more smooth and profitable. So please try to speak to your supervisors as much as you can. Okay? That's a very important thing if you are graduate students, and if you are going into the academic field. It's very important to discuss with other people and communicate. So the first thing that you should do is you have a good communication. You should have good communication with your supervisors. So as I said, he was doing the theoretical part of vibrational spectroscopy, but I did not like theory, and I was an experimentalist. So I had no suggestions, real suggestions from him, but I liked him because he liked science. And he was always saying that it's very enjoyable to do science. So I learned that from him, that then I liked science, and I really enjoy being a scientist for a long time. So your supervisors are very important for your life. So this is an example of Raman spectrum of benzene. So you are chemist, you know benzene. And if you shine your laser into benzene and use a spectrometer, then you get this kind of nice, very colorful spectrum. Because Raman scattering appears with different energy, or it's called Raman shift, then the color changes, of course. Okay? If you come back to the previous one, here it's overexposure, so it's white. But you know, here it's more violet, here it is more blue, and here you may see green. Okay? But if you go further, then it becomes yellow and even red. Okay? So in the case of carbon tetrachloride, the energy shift is very small, so the color change is very small. But if you go to the very far away with larger energy shift, then the color goes to yellow and red. So this is what you see here. Okay? Green to red. And here you have many lines. So this is a spectrum. If you compare this spectrum with this picture, then you can understand what we are doing. So here we are plotting. Here we are using wave numbers for the unit. And this 0 is a position where the original laser line is. And it's not wavelength, but a wave number. So the scale is a little different. And here we have the Rayleigh scattering with a shift of 0. And then we have, say, 1,000 wave number, 2,000 wave number, and 3,000 wave number shifting from the original band. And because here you see very weak green line, in this case we use a green laser for the excitation. And we use a special filter to eliminate the laser line. So it it looks very weak. But without a filter, it's very, very strong. And it's really strong here. But it is now eliminated. So here we have this band, very strong band. And I'll show you later, this band comes from the vibration called breathing vibration. Breathing means the whole benzene ring vibrates like that. And here you have another strong band, which has a shift of 3,000 wave numbers that comes from the CH, stretching motion. So benzene has 6 hydrogen atoms. It stretches like that. So if we have a band around 3,000, we immediately know that this is from CH stretch, because the CH stretch force constant is common to most of the molecule. So the frequency of CH stretch is determined by that force constant. Then CH stretch always gives bands around 3,000. So this is how vibrational spectroscopy works. You know the origin of the vibration, and then you can predict the wave number that you see by Raman spectroscopy. So by comparing your observed spectrum with your theoretically predicted spectrum, you can tell in many details of the molecule and molecular structure. So this is how we have the spectrum like this from the picture or the spectrometer output. So why Raman scattering occurs? So here I show you a very simple classical picture of vibrational Raman scattering. So this is incident light. Is this okay in Chinese? You understand? So incident light. So it vibrates, the electric field of incident light vibrates like that, the simple cosine function with angular frequency omega. Okay? Then it collides with a molecule, and then it scatters Raman scattering or Rayleigh scattering. And here, this is misprinting. This should be small omega. So this one should be small omega. So the scattered light has got the angular frequency of small omega and small omega minus large omega, or small omega plus omega. This is Stokes-Raman scattering. This is anti-Stokes-Raman scattering. And here omega is the angular frequency of the molecular vibration. Okay, so why? So the incident light electric field can be expected like that. And then there is some electrons in the molecule. So if you have the electric field applied to the molecule, then the electron inside the molecule is affected the electric field. And plus goes to the minus side and minus goes to the plus side. And if the polarity reverses the, because this one is vibrating, then it goes to a different, another way. So that means there is some dipole moment induced in this one, okay, according to the oscillating electric field. And the dipole moment induced by the incident light can be expressed as here. So induced dipole moment is equal to alpha. Alpha is the polarizability. Polarizability is a quantity that represents how movable the electrons are in the molecule. If polarizability is large, then electron can move very much inside the molecule and then makes a larger induced dipole moment. And usually the polarizability corresponds to the volume of the molecule in which electron can move. So if polarizability is very large, then electron can move in a long distance and resulting in larger induced dipole moment. So this is a formula showing that. And the polarizability can be expressed like that because molecules are vibrating. Then if the molecules do vibrate, then the volume changes. Okay? So the polarizability is expressed as the sum of the constant part and also the oscillating part because the volume changes with time, like this. And here the large omega is the angular frequency of the vibrating molecule. Okay? So if we introduce this electric field here and this polarizability here, then you have this result. And because you have two cosines, cosine small omega t and large cosine omega t, from that you have small omega plus omega and small omega minus omega. Maybe you learned it in the high school days. The product of cosines gives omega plus minus omega. And also from this part, you have the same frequency. So the same frequency part corresponds to Rayleigh scattering with small omega. If you have oscillating dipole with small omega, that means the light with angular frequency small omega is emitted from this molecule. Okay? So then you have this component oscillating with small omega minus omega. That is Stokes-Raman scattering. So you have a shifted frequency by omega. Okay? Large omega. Large omega is the angular frequency of the molecular vibration. And also you have the term small omega plus large omega that corresponds to anti-Stokes-Raman scattering. So it is a very simple picture. Incident light, affects the molecule, and the molecule is vibrating. So there is a sum and the difference part of the frequency, which corresponds to Stokes and anti-Stokes-Raman scattering. So it's a very simple way of explaining Raman scattering. And you can learn more in detail in quantum mechanics later if you want. And there is a formula called Kramers-Heisenberg-Dirac dispersion formula that explicitly expresses Raman scattering process. But for now, it's enough to know that we have both Stokes-Raman scattering and anti-Stokes-Raman scattering. And we usually look at Stokes-Raman scattering. Now, I come back to here. So there are many different molecular vibrations. In the case of benzene, here I show you 3 different vibrations of benzene that you see by Raman spectroscopy. I just show you 3 bands, this one and this one and this one. And this one, as I said, is a breathing vibration in which the whole ring expands and shrinks like that. And the frequency or angular frequency is about 1000 wave number. Then here, as I said, this is a CH stretch vibration. If you see here, hydrogen is stretching and shrinking, stretching and shrinking. So it should come around 3000 because it's CH stretching. And here you have a CH bending vibration around this wave number. So all the other small bands are all assigned to those molecular vibrations. And I can show you how we do that. So you don't have to memorize all of these, but this kind of analysis already done very nicely, both quantum mechanically and classical mechanically. And we now know which vibration gives which wave number. And this is called normal modes of vibration. And any kind of vibration of the molecule can be expressed as a linear combination of those normal modes. Okay? So these are the very fundamental vibrations. And in spectroscopy, we only see those normal vibrational frequencies or wave numbers. So what we see is the wave numbers of those normal modes. Okay? But I'm not going into the very details of this kind of analysis, but please do understand that we all know the normal modes of vibration, benzene like that. Now, what kind of applications? First, I show you a very fundamental application to structural chemistry. And this was done by Professor Mizushima, my scientific grandfather. So I showed Professor Shimanouchi as my supervisor, but Professor Mizushima was the supervisor of Professor Shimanouchi. So he is my scientific grandfather. Then what, not he, but his group, what his group did was to discover the rotational isomerism. And you all are chemists, so you know what rotational isomerism is. So here I show you 1,2-dichloroethane. And you have 2 chlorine molecules, and you know that there are 2 internal rotational configurations. One is called trans, and the other is called gauche. And nowadays, many people use anti. But in physical chemistry, we use trans and gauche. And trans and gauche are actually named by Mizushima. And as you know, this is a Newman projection. You all know Newman projection? So in the case of trans, you have the 2 chlorine atoms at the 180 degrees. And for the gauche form, it's 60 degrees. You know this? And this was found by Mizushima's group using Raman spectroscopy. And here I show you first the Raman spectrum of liquid 1,2-dichloroethane. So here you see 2 bands at 754 and 655. And these vibrations are due to the CCl, stretching vibrations. And because you have 2 CCl, then the combination of the 2 CCl makes symmetric and anti-symmetric combination of the stretching mode. And this is a symmetric and this anti-symmetric stretching mode. So there are 2 CCl stretch modes. And then it happened that a student in Mizushima laboratory was doing new experiment to measure the liquid 1,2-dichloroethane at lower temperature. And he did some experiment, but somehow he left the experiment and went out and came back, many hours later. And he found that the sample was frozen because he cooled the sample too much. But he found that the spectrum he got like that. Eventually, the crystalline 1,2-dichloroethane, one band was missing. Okay? All the other bands are there, but this band was missing. So why? Why this band missing? Then they did a lot of experiments to find out that in the liquid phase, 1,2-dichloroethane exists both in the trans and gauche form in the equilibrium. So you have 2 bands like that, trans and gauche form. But if you go to the crystalline state, because of the packing of the molecule, only the trans form to exist. So gauche molecules is not existing in the crystalline state. So if you know the answer from the first, it's very easy to interpret this result. But it was not easy for them to come to this conclusion. But they do many, many things to finally conclude that the two conformers transcend Gauche in the liquid phase, but only one transform in the crystalline state. And then, by that time, chemists believed that there was a free rotation around the CC bond. Okay, because you are taught in the textbook that there are transcend Gauche structures, you know that. But before that, no one knows about the internal rotation. And many people did believe that CC bond was freely rotating. But they showed that it's not like that. There is some preferred configuration which they named transcend Gauche. And that was a really big discovery in the structural chemistry. Because without this kind of internal rotation or rotational isomerism, you never have the higher order structure of proteins or nucleic acid. Maybe you know the structure of proteins which have highest order structure. That comes primarily from the rotational isomerism around the CN bond, amide bond. And amide bond has got a preference in the internal rotation angle. Maybe you know what's called the Ramachandran plot, in which the two angles are plotted in proteins. So only if you have a preferred internal rotational angle, you get the higher structure of proteins and nucleic acid. So this is a really epoch-making discovery in structural chemistry, in which there is a preference of some configurations in the CC bond. And I believe this work deserves 2 or 3 Nobel Prizes, but unfortunately Japan was having a war with the Western world, and the discovery was done during the war, and it was never appreciated properly after the war. So unfortunately, he did not get any Nobel Prize, but this is a really big discovery of structural chemistry done by Raman spectroscopy. And this is a structural chemistry application. And this is another biochemical application. Here I show this guy, Professor Miyazawa. He's my scientific uncle. And Miyazawa was one of the persons who analyzed the spectrum of proteins. So this spectrum is a protein called subfragment 1 of rapid myosin filament. So don't worry about this name. So protein has got this kind of spectrum, very complicated. But many studies just elucidated what these peaks are. And among those peaks, there are 2 characteristic bands called amide 1 and amide 3, which was analyzed this person. And we now know that if this peak of amide 1 is observed at 1655, then the protein has got the alpha helix structure. If the peak is at 1670, then the secondary structure is a beta sheet. And if it's at 1660, it's a random coil, you know, helix and beta sheet and random coil in the protein structure. And also this band amide 3 has got similar information. So if you just measure the Raman spectrum of a protein, then you can tell what kind of secondary structure that protein has. And that kind of thing you can do even from living cell. I'll show you later how we do the Raman spectroscopy of living cells. But if you measure living cells and get the protein Raman spectrum, then you can tell what kind of secondary structure the protein in the cell has. That can never be done by any other method. So now there are many, many biochemical applications of Raman spectroscopy based on this kind of interpretation. Now I show you photochemical application, and I'll tell about this later in more detail, but this is a transtyrubine molecule, and transtyrubine is one of my favorite molecules, and I've been studying transtyrubine for maybe 20 years or so, and it's a very interesting molecule. But here, what we did was to photoexcite the styrubine molecule with what we call pumping. Pumping means making the molecule from the ground state to the excited state. And then in the excited state, there are many photochemical things happening. And we trace what's going on in the excited state by using the probe laser, by Raman spectroscopy. So it's called a pump and probe spectroscopy. And the lifetime of transtyrubine in the excited state is only, say, 50 picoseconds or something. Very, very short time. So we need high time resolution. In this case, we are doing picosecond Raman spectroscopy. That was my favorite field 20 years ago. And we constructed a system to do picosecond time-resolved Raman spectroscopy and looked at the spectral changes of, say, 0 picosecond is just the photoexcitation. And what happens after 2 picosecond, 3 picosecond, 10 picosecond, 30 picosecond, 50 picosecond, after the photoexcitation, what happens? So by doing this, you can tell what kind of changes do occur after the photoexcitation to the molecule. So you really want to understand the photochemistry in the excited state. It's very, very useful to use this kind of time-resolved spectroscopy to understand the changes in the excited state. So I discuss a little much more in details later of this one. So this is an obvious application and easy application, I should say. So this is a medical application. And this is shows the Raman spectrum of cancer and normal human lung tissues. We collaborated with a doctor, and after the surgery, we have a cutout of a small piece of lung tissues from a human patient, and then measure the Raman spectrum for this point from 1 to 7, like that. So here I show you 1 to 7. These are the spectra you measure from these different points of the lung tissue. Okay? And then here I show you the spectrum, average spectrum of 300-400 samples of normal lung tissue. So the normal lung tissue has got this Raman spectrum. And here I show you the red one is the average of also 300 to 400 cancer tissues. So this is a standard spectrum from the cancer. So there is a difference between red and blue. And the difference comes from the fact that in the cancer Raman spectrum, you have stronger band, that amide 1, as I mentioned. The amide 1 comes from the protein. So that means in the cancer tissue, there is more content of proteins. So if the cancer is generated in the lung, the cancer cell produces a lot of proteins. And then the protein is more rich in the cancer Raman spectrum than in the normal Raman spectrum. Then you can make a distinction between cancer and normal tissues by Raman spectroscopy. And if you see the point 1, the spectrum is like this. So it's very close to the normal spectrum. But if you go to 2, then you have this spectrum, which is quite different from this one and resembles here, stronger amide 1 band. And then if you go to point 3 the same, 4 the same, and 7 the same. So the Raman spectroscopy tells you that here at point 1 we have normal tissue. But here at 2 you have cancer. So in the surgery, it is very important to determine the boundary of cancer. If you cut out normal tissues, in very big normal tissues, that's not good for the patient, of course. But if you cut in a smaller size, then there is some remaining cancer. So it is very important to cut the real boundary of the cancer, to take out cancer, but leave the normal tissues. So in this case, the doctor probably did it quite nicely. Okay? Most of the part is cancer. The only small part is normal. So if there is a half normal part, then that means the doctor was doing badly. So we are now planning to do Raman spectroscopy during surgery to find out the boundary of the cancer. It's not a basic research, but we can apply Raman spectroscopy, at least in principle, to that kind of applications. So this is medical application, quite easy. And I can show you much easier one. This is a food science application. And maybe this is sashimi. And there are different types of sashimi. It's called toro. Maybe you know that. Toro is the most expensive and most delicious part. And lean is the not so delicious, but delicious. And here we can just measure these different parts. And here is the content of the fat or lipid contained. So in the toro part, we have a lot of lipids. That makes toro so tasty. You can see this white color that comes from the lipids. But if you go to lean, it's very small. And you can actually use this kind of portable Raman spectrometer, which is, the computer is the same as this one. So this is a spectrometer of this size. And this probe is just this size. You just shine your laser like that and get the Raman spectrum of those tuna. So we are now collaborating with some people to carry it into some market or fish market or something, and to measure tuna, to evaluate the value of the tuna, something like that. And finally, this is one of my former students working in her place using Raman. This is Raman probe, and measuring the meat. And she found that Raman can be used to make distinction between pork and beef. And there are minced meat, which they sell by saying that it's beef, but they sometimes porks are mixed. But if you do Raman spectroscopy, you can make the distinction between pork mince and beef mince quite nicely. So that kind of daily kind of application Raman can do. Okay, so this is just a brief brief introduction to Raman spectroscopy, and now I show you how we do Raman spectroscopy by showing some pictures. This is one of the Raman spectrometers that we have in laboratory, the basement. And here you see the Russian mafia in a group. He's Vitaly Korepanov, a postdoc working for us. So this is the whole Raman spectrometer, like that. So here we have the laser, and here we have spectrometer and sampling optics. So now I'm just pretending to work in the lab. But this is a laser. This is a neodymium laser of this size. So the laser beam is guided like that. And here we have the sampling points. And this is a sampling, this is a spectrometer. This is a collecting optics. You collect the scattered light like this. And this is a cell which contains some liquid sample. And in order to avoid heating, we want to rotate the cell like that. So we spin the cell by using this motor here. So the cell rotates like that. And then we put the cell. Then this is a lens collecting light scattering. Here the laser beam comes from the bottom and focus into the sample here. So here you have the focal point. The scattering light comes to this direction and then collected by this lens and going into the spectrometer. So here is a sample, the collecting lens, and then the image is made on the entrance slit of the spectrometer. And then this is a spectrometer. And if you open this one, this spectrometer, this is the inside of the spectrometer. And here you have entrance slit, and you have mirror going this way and going out like that. Here you have a very small prism. And here we are working in the deep ultraviolet region. So it is not easy to have nice grating for this purpose. We are using prism for this spectrometer. But I'm not going into the details, but inside of the spectrometer is like this. Then the next one, we have another spectrometer connected to the previous one. The first one is used to filter out Rayleigh scattering, and second one is used to disperse light to get the Raman spectrum. So again, inside. In this case, here we have a turret, and we have 3 gratings. And we can change the gratings by rotating this turret. And here you have the entrance slit, and this mirror coming here, and maybe going out this way. And here I show you a CCD detector. CCD is an abbreviation of charge coupled device. And you may know CCD because in your smartphone you have CCD to take pictures, okay? And in this scientific use, CCD is cooled down to very low temperature by using liquid nitrogen. So this detector has got a liquid nitrogen reservoir. So we pour liquid nitrogen from head and to cool down the detector so that the thermal noise can be reduced very much. Then finally we got a computer to analyze the spectrum like that. So if you do Raman spectroscopy, eventually you get this kind of spectrum. Then I'll show you something about Raman microspectrometer, which means we do Raman spectroscopy under microscope, and we can see, say, cells or the small particles or whatever under microscope and do Raman spectroscopy. So here we have the microscope, and here we have the spectrometer, so on. Yeah, this is the laser part, 2 lasers, and then it's introducing into the microscope, not very clear. This is a microscope. So the beam comes from here and goes to the sample, and then the scattered light back is collected by the same objective lens and going into the spectrometer. I'll show you the details later. Then this is the spectrometer part, and also spectrometer. Now that this is a CCD, much smaller than. In this case, we do not cool the detector by liquid nitrogen, but we cool it by thermoelectrically by using Peltier effect. So this is the last output. So by showing this, I'm telling you that in physical chemistry, we usually construct the spectroscopic system by ourselves. So by doing so, we have a very unique system. You know, all the two Raman spectrometers are probably of the best quality in the world. You can never buy that. If you buy commercially available apparatus, maybe the quality is much lower than what we have here. So it is very important to make everything by yourself. Okay? So what we do here is a real state-of-the-art and world-leading Raman spectroscopy in Jauda here. Okay, so I now stop here and have a 5-10 minute break. So Shoshi Isha. Okay, let's start the next. So I first speak about time-resolved Raman spectroscopy. And actually, I'm using the material which I used last year when I was invited to Germany as a Carl Zeiss lecturer. And I gave 5 series of lectures on Raman spectroscopy there. So I'm using the same material for this lecture. So what is time-resolved Raman? And as I said, we use 2 lasers. One is a pumping laser to excite the molecule in the excited state, and use a probe laser to probe, to see what's going on in the excited state of the molecule. So I first show this one. And time and space. When and where I'm saying, this is a sunset at a lake called Shinjiko Lake in Shimane Prefecture, Japan. And you can see this kind of very beautiful scenery only at one certain time, say 5:30 or something. If it's 1 minute later or 1 minute before, you can see this. So the time resolving is very important to see something important. So in the case of time-resolved Raman spectroscopy, we want to see the molecule doing some reaction or something. So when the molecule is in action, we want to see it. So this is like a stopped motion picture. And as I said, I like to play tennis. But if you want to play tennis better, you want to see how you hit the ball. And if you hit like this, and then if you see the face of your racket properly or not, then you can tell it's good or not. So that kind of stopping motion is very crucial. The same is true for the molecule. So we want to see the molecule in stopped motion by time-resolved Raman spectroscopy. And so here I show you that now I'm going to speak about Raman spectroscopy in this region, the molecule or atom or molecular complex in a very small world molecule in which the size is less than 1 nanometer. And then the dynamics there, characteristics times there is picosecond or even femtosecond. Very, very short time scale. The change is happening very, very rapidly, and we want to trace that. So this is one example that should be of interest to you. This is a result of time-resolved Raman spectroscopy to elucidate the structure of the molecule called diphenylacetylene. So this is diphenylacetylene. And if you do Raman spectroscopy of the ground state, S0 state of diphenylacetylene, this CC triple bond gives the wave number at 2223 wave numbers. And if we know this frequency or wave number, then we immediately can tell that it's triple bond. Because the triple bond has got a very large force constant, and that gives higher frequency. For example, CC double bond gives about 1600, and CC single bond gives 1000 or something. So as I said, the Raman spectrum, the molecular fingerprint, and if you see this wave number, then you can immediately tell that it has a triple bond. So it is very natural that diphenylacetylene has got triple bond because it's acetylene derivative. But if we photoexcite this molecule in the excited state, which is called S2, the second excited state, electronic state. Do you know S1, S2? S1 is the lowest excited singlet state. And maybe I show you the next picture. But anyway, in the second excited state, then time-resolved Raman tells you that the wave number is 2099 wave number. So this is also a little smaller than this one, but is still in the range of the triple bond. But if you look at this one, we are very surprised that in the S1 state, the lowest excited singlet state, the wave number was 1567. The 1567 is the wave number of the double bond. So we found that in the S1 state, the diphenylacetylene takes this kind of structure. It's very similar to styrene. If you have two hydrogens here, it's styrene, and it's a double bond. We are very, very sure that this is double bond because of this frequency. And if you come down to the triplet state, the wave number comes back to 1974, and this is also a triple bond. So you call this molecule diphenylacetylene, but it is acetylene only in these states, but not here, because this is double bond. There is no triple bond involved in this molecule. So this is what can happen in the excited state. In the excited state, electrons are in a very different orbitals, including anti-bonding orbital. If the electron is excited anti-bonding orbital, then the bond order is reduced, say from triple bond to a single bond like that. Then there is a more chance of chemical reaction proceeding because you have the unpaired electron like that. So by looking at the excited state, we have a hint where we can elucidate how the reaction proceeds in the excited state. But it never happened in the ground state. Okay, this is how we use Raman spectroscopy and read the spectra to know the structure of the molecule. Next example, here I show you how does chemical reaction proceed. You know, from the starting molecule to the product molecule, you have some excited state. So we want to know what happens here. The usual thing that we see here, but we rarely see here. So when and where this reaction actually proceeds. So here I show you the excited state. So in the ground state, you have the singlet state. Singlet state means if you excite an electron, the electron in the ground state is in anti-parallel. And if we excited one electron, it goes with the same direction of the spin, and then the total spin is 0 because it's paired. Okay? So it's a singlet state. But if in the excited state, the spin can be reversed to this direction, then you have the triplet state. So at first you have the excited singlet state. The lowest one is called S1, singlet, lowest excited singlet state. A second excited state is called S2 state. And but if the electron spin is reversed, then you got a triplet state. And all these are the excited states. Here are the singlet excited electronic state, here are the triplet excited electronic state, and here you have the excited vibrational state in the ground state. And reaction occurs in these excited states. So we want to know what are the structures of molecules in the excited state and what are going on there. So we do time-resolved Raman spectroscopy, chemical reactions. So this is an apparatus that I first constructed in the year 1984. So that means 30 years ago. And at that time, laser called neodymium YAG laser, a nanosecond laser, was commercially available, and we used that laser to construct this kind of system. And we believe that we led the world by doing this time-resolved spectroscopy. And one interesting point is that we used this kind of liquid nozzle jet for using sampling of the system. So we have the solution of sample ejected from a nozzle into the air, making a very nice optically flat film, and with spectroscopy of that. Because the pulsed lasers are very strong, and if you have a cell wall, then it easily damages the glass. It burns up the glass. So I thought how we can avoid the damage of the cell wall. The solution was that we do not use the cell. Okay? So I tried to use this nozzle jet, just ejecting the liquid into the air with the form of film. Then you have no cell windows, and we did a very nice time-resolved Raman spectroscopy with this system. So I'm really proud of constructing this new system with this sampling. And this is a very fundamental photochemical reaction of benzophenone. And maybe you learned this in your lecture of photochemistry. And benzophenone is this molecule, two benzene ring and carbonyl. And for example, if you dissolve benzophenone in isopropyl alcohol and put it in the daylight, and if you wait for a day or two, then you get a reaction, and you eventually get benzophenacol, crystalline benzophenacol. Have you ever tried that? It's a very famous photochemistry experiment, and every textbook of photochemistry mentions this kind of reaction. So benzophenone is very stable, but if it's irradiated by light, it reacts and makes this final product, benzophenacol. So what happens in the excited state? And people, by many experiments, made a guess. It is occurring in the triplet excited state. Okay? So before doing excited state spectroscopy, by using many photochemical approach, they made a guess that the reaction takes place in the triplet state. But why in the triplet state? There was no answer for that. So we used time-resolved Raman spectroscopy to look at benzophenone in the excited triplet state. What we did was to use the pump laser, nanosecond laser, at 266 nanometer with a 5 nanosecond duration. Then the benzophenone molecule is excited to the S1 state. And then the intersystem crossing occurs immediately, and then you have the triplet T1 state populated. So after photoexcitation, 15 nanosecond delay, then all the benzophenone molecules will be in the triplet state. And then we shine another laser, green laser, to monitor the triplet spectrum. And we use what's called resonance Raman scattering, in which we use the exciting laser line that has the same wavelengths as the T1 to Tn electronic absorption band has. So we photoexcite the molecule in the electronic absorption band. So by doing that, we can have the resonance Raman effect. And then the intensity of the benzophenone, the triplet state, will be enhanced by order of 10 to the third or 10 to the fourth, and we can easily see the Raman spectrum, the triplet state. So the result is here. So in the probe only means we do not excite benzophenone. So we just see the solvent bands, which is carbon tetrachloride, and whose spectrum I showed, in the very beginning. So this is a very huge solvent band of carbon tetrachloride. And if you pump the molecule, so this is called a pump and probe, then you have some extra band coming out here very clearly. That shows the effect of the pumping. The effect of pumping means benzophenone goes into the triplet state in this case. So this is actually the Raman spectrum of the triplet benzophenone. If you subtract this solvent band from this one, you get this spectrum of the triplet state benzophenone. But this was not observed in the ground state. Why? Because of the resonance effect. So this experiment, we use, say, 1 millimolar concentration of benzophenone in carbon tetrachloride, then the low concentration, in the ground state, then you do not see any benzophenone band. But you photoexcite, then it goes in triplet state, and then the triplet state is in resonance with the exciting line. So there is a resonance Raman effect occurring, and the Raman cross-section is 10 to the third or 10 to the fourth time higher. Then you see the Raman spectrum. Okay, so sometimes it is called time-resolved resonance Raman spectroscopy. It's called TR3. But anyway, we observe the triplet excited state of benzophenone like that. So how do we interpret this one? What we did was to assign the bands. So this is many different isotopically substituted benzophenone. Here, all the hydrogens in the two phenyl rings are deuterated. And here we have the one ring deuterated, and here we have carbon-13. And here we have only the hydrogens in one ring deuterated, and here we have only the carbon-13, or centered carbon here, the substituted with carbon-13. So a student did all the synthesis of these isotopically substituted benzophenone and measured the triplet spectrum, and found that the effect of, say, carbon-13 substitution, all the other parts are very similar, but here you see this band, 1209 in the D5 goes to 1186 for carbon-13. So all the other bands are the same, but only this band shifted. So that means this band is affected by the substitution of carbon with carbon-13. So by doing that, we want to assign where the CO stretch band is observed. Okay? You also see from here H10 carbon-13, and you remember we have the H, here we have the H non-substituted benzophenone. And from this result, actually we assigned this band. This band should be the CO stretch band. Okay? This is very, very unusual. I show you this one. So in the ground state, we have this structure, and this band, CO stretch, is observed very strongly at 1685. This is, as I said, the double bond stretching frequency. But in the excited state, we do not see very strong peak around here. And by isotopic substitution, we found that these features did not change with the carbon-13 substitution. If you have the CO stretch band around here, it should be affected by carbon-13 substitution. Okay? But this band, very weak, but here, this shifted by carbon-13 substitution. So we concluded that in the triplet state, the CO stretch motion, stretch vibration, has a frequency of 1222 wave number. So it is much, much lower than the double bond frequency. And as I said, the CC single bond is around 1000 wave number. And this is the CO stretch in the single bond region. So in fact, in the excited state of benzophenone, this double bond is practically a single bond. And electrons of the bonding is localized on the oxygen atom and the carbon atom and makes a kind of biradical. You know biradical? Two unpaired electrons from here. Okay? So this is what I showed, like this. So in the excited state, this can happen. So in the case of benzophenone, it was originally the CO double bond, but it goes to the CO single bond with two unpaired electrons on carbon and oxygen. So we now know that in the triplet state of benzophenone, this CO bond is single bond with biradical structure. And if biradical structure, it's very reactive. It's very reasonable because you have the unpaired electron to react. Actually abstract hydrogen from other molecule. So now we finally understand why the reaction takes place in the triplet state. In the triplet state, the benzophenone molecule is ready for reaction by making this bond a single bond and biradical. So by this way, looking at the excited state by time-resolved Raman spectroscopy, we can elucidate how the reaction proceeds. This is one example. Then I tell you another example. This is styrene, as I already mentioned. This is the photoisomerization transtyrene, in which we do more detailed analysis of the reaction process. And it's a bit more advanced and a little bit more difficult for you to understand. But I try to explain as easily as possible. So if you have any questions, just please stop me and ask questions. So styrene has got two structures, trans and cis, you know. And then trans molecules is a crystal or powder at room temperature, and cis styrene is a liquid. So they can be separated quite nicely, and you can think that these are two different molecules. So at room temperature, it never, be transferred from trans to cis or cis to trans. And here I show you a potential curve, that's just a cartoon. Here the torsional angle is with respect to this bond. So trans structure means the dihedral angle is 0 degree, and in the cis form it's 180 degree. And because there are very high potential barrier, then the trans form never goes to cis, and cis molecule never goes to trans at room temperature. Okay? They are well separated. because you have the double bond here, so double bond has got one sigma bond and one pi bond. So the rotation is hindered because of the pi electron. Okay? So you do not expect any rotation around the double bond. Maybe you can expect rotation about single bond, but never on the double bond. So that's the reason why you have the very high potential barrier. But photochemists found that if you photoexcite trans-silver molecule in the excited state, in this case S1 state, then it goes to cis state somehow. So this is called photoisomerization. Isomerization means trans goes to cis. So this is a very, very simple chemical reaction from this molecule to this molecule and unimolecular reaction. So many, many physical chemists studied this system by using ultra-fast spectroscopy, and still there are many physical chemists studying this system to understand more about the chemical reaction, how it proceeds. Okay, so if we photoexcite this molecule in the S1 state, somehow the rotation occurs, and the scheme, expected by these photochemical people is that in the excited state somehow the rotation occurs, and then it goes into the state called perpendicular state, perpendicular or phantom state, in which you have the 90 degrees twisted structure, and then it comes down 50% back to trans and 50% go to cis. By the quantum yield measurement of the photochemical reaction, they do know that if you excite 10 trans molecule, 5 comes back to trans and 5 goes to cis. From that fact, they make they deduced that the mechanism is like this. But here, somehow rotation should occur from the double bond to the planar structure to the perpendicular structure. Why it happens? And there are many theories that tells in the excited state of double bond, one electron is transferred into the anti-bonding state, and that makes the bond single bond, as you saw from the benzophenone and diphenylacetylene case. If it's a single bond in the excited state, then it can rotate. So many people first thought that in the S1 state, the central bond is a single bond, but no one actually proved that by experiment. So I wanted to check whether this is really a single bond or not. And also it is very well known that this reaction rate depends very strongly on the solvent. So the reaction proceeds in 70 picoseconds in hexane, but it proceeds in 120 picoseconds in dodecaine. And people did believe that this is because of the viscosity of the solvent. You know the viscosity? In a viscous solvent, molecules are more difficult to move. So for the internal rotation, if it takes place, then in more viscous solvent, it is slow. And less viscous solvent, it's fast. So because viscosity of dodecaine is much larger than hexane, so it may be caused by the viscosity. So maybe 30 years ago or something like that, people believe like that. So it is single bond here, and the viscosity makes this solvent dependence. But I wanted to see what happens in the excited state by time-resolved Raman spectroscopy. So this is the first spectrum I got. This is 30 years ago. And we are really glad to have this spectrum. And here you have the solvent only. This is pump and probe. And this is a spectrum of the S1 state of still being. And here we have many bands in the S1 state. But we have no way of assigning this band. So if it's a single bond, central CC bond is single bond, maybe we should see something here. Okay? So what we did was also the same thing. We prepared a carbon-13 substituted trans-tubine. So we just substituted 2 carbons here. So if it's a central CC stretch, then the frequency should be affected by the carbon-13 substitution. Then we found that this peak shifted, but all the other peaks remain the same. So that means this is a central CC bond with a wave number of 1570. So 1570 is a wave number of the double bond. Okay? So it's not a single bond as expected by theory. So this is a new finding of this result. And then the question arises, it's a double bond, but why it rotates? So then the story continues. And so we wanted to make more precise measurement. After 10 years, I moved from the University of Tokyo to a new institute, and fortunately got a lot of money and a lot of people to work with. And we had this gorgeous system, and at that time Japan's economy was in a very good conditions, and they provide a lot of research money and new investments. And all these lasers are very, very expensive, but I was lucky to afford these apparatus, and good people from all over the world, and got a nice laboratory and constructed this system. It's a picosecond time-resolved Raman spectroscopy, and I think this was the world best system at that time. Unfortunately, now the world best system in Britain, because it needs a lot of money to maintain this one. So this is a detailed block diagram of the system, but I'm not going into the details. But we need many laser sources, dye amplifiers, and harmonic frequency generators, and many optical devices to do the experiment. And what we do was to first use 2.2 picosecond pulse at 294 nanometer, then photoexcite still being excited state. This is a pumping pulse. Then use 588 nanometer 3.2 picosecond pulse to probe the resonance Raman scattering of the S1 state. So here I show you the relationship between the laser wave number width and the pulse width. So if you go to a very short pulse, because of the uncertainty principle between energy and time, then the very fast pulse has got large wave number width. So it's an uncertainty principle like that. It's called a transform limited relationship between the laser line width and the pulse width. And here you have if you have 1 picosecond laser pulse, then your laser wave number is about 10 wave number. And 10 wave number is probably too large for doing precise Raman spectroscopy. So if you want to very high resolution of 1 wave number, then you have got only 10 picosecond time resolution. So in the apparatus I showed, we optimized both the laser line width and the pulse width with pulse width of 3.2 picosecond and wave number width of 3.5 wave number. So this is what's called transform limited. So we optimize both of the characteristics of the pulse and do time-resolved Raman spectroscopy. Yeah. Then we can determine very accurately the peak position because we have the pretty nice resolution. So this is the results. So we use the 294 pumping and 585 for probing, and this spectrum resembles very much with what I showed later, previously, 10 years back. And again, we found that CC stretch vibration is around 1560. So it's a double bond, definitely. So I repeat the question, why rotation occurs around the double bond excited state? So in order to solve this problem, we are reminded of the fact that the reaction rate is very much dependent on the solvent. Okay? So we thought that if we look at this vibration with different solvent, there might be a key for the understanding of the chemical reaction. So what we did was to measure this band precisely in different solvent. So this is the result. So here we are getting very, very physical chemistry oriented matter. So this is a CC stretch Raman band all around here at double bond frequency. And if we measure in hexane, we have this band shape. In heptane, this one, octane, this one, nonane, this one, hexadecane, this one. And you see there is a peak shift of hexane to hexadecane. And also the bandwidth here, it's not very obvious, but bandwidth decreases on going from hexane to hexadecane. So the difference is very small, definitely different. And we did many experiments. So the peak position shift to higher wave numbers and the bandwidth decreases on going from hexane to hexadecane. So we found this. Why? It might be related with the mechanism of the chemical reaction rate depending on the solvent. So this is a plot of peak position bandwidth of the same band measured in hexane and octane and decane in different temperatures. And we plotted the peak position of the y-axis and the bandwidth to the x-axis. And we are very surprised that all the data were on this very nice straight line. And why peak position and bandwidth so much related nicely, we had no reason at the time to explain. Then, why does linear relation hold? And also, if you plot the peak position against the rate of isomerization, this is determined by fluorescence, time-resolved fluorescence spectroscopy, then we are also surprised that it makes very nice straight lines at different temperature, and it converges to one point very nicely. That's very strange. So in order why does linear relation hold, and why does line converge here? This is totally a new result, unexpected. So we have to solve that. Then we actually make a theory to explain these results. This is a theory of vibrational dephasing and band shape. And if you have the Raman band, the peak position corresponds to the vibrational frequency that I already mentioned. But the bandwidth comes from the dephasing of the vibration. So dephasing means how the phase relation is lost. So if the vibration, your molecular vibration, vibrates with the same frequency forever, then it is very sharp, no width. But if the vibration is stopped somehow, disturbed by solvent or some other reasons, then it becomes broader. So the width comes from how the vibration is dephased. In other words, the width reflects the interaction of the molecule with other environmental things, the molecules, solvent molecules, and so on. Okay? So we try to understand what causes the dephasing of the vibration. And here I show you one theoretical approach in which we are using acetone and acetonitrile as the simplest, solvent and solute. So here we have acetone here. Here you have the methyl group, and here you have CO, and here you have the methyl group. So two methyl group with CO. And here you have the acetonitrile. Here you have the methyl group and carbon and nitrogen. And we do some molecular dynamic simulation of the system. What we want to calculate was first the dipole moment of this acetone molecule. In every textbook of organic chemistry, you have carbonyl with delta plus and delta minus, and the reaction always, occurs when you have the delta plus attacked by some reagent. So this kind of explanation was always there in the textbook of organic chemistry. But here we want to know what is the magnitude of the dipole moment on the CO bond. Okay? And if the CO bond is polarized, it becomes closer to single bond, then the frequency is decreased. Okay? If you have no polarization, it's double bond. So that means if the dipole moment changes, then the frequency changes. Then if the frequency changes, it causes a dephasing. Because if it vibrates with the same frequency, then the phase is maintained all the time. But if the frequency changes, then after some time, the phase is shifted from what should be with the constant frequency. So it causes this dephasing of. So by calculating this kind of fluctuation of dipole moment and frequency, we can calculate the bandwidth of the band. And actually, we did a measurement of acetone, acetonitrile, and found that the simulation reproduces the result very nicely. So this is very in detailed story, so I'm not going into that. But I can show you a movie. So this is a result of calculation. And at the center, you have the acetone molecule. And here you have the carbon and oxygen. And all the others are acetonitrile molecule. And the methyl is now represented with just one ball. Okay? And here I show you the dipole moment and probably the frequency. You can think it's frequency with time change. So this is 0 picosecond, 2 picosecond, 4 picosecond, 6, 8, 10 picosecond. And then this red one shows the value of dipole moment. Here you have very big dipole moment, then it's red and blue. So plus is here and minus is here. And then if it comes down, then it's neutral. Okay? So that is caused by the fluctuation of the solvent surrounding the molecule. If the solvent is somehow aligned to prefer the polarized structure of acetone, then the delta plus and delta minus becomes large. But if it's the opposite, then now polarized, then not polarized. You understand? Then according to this fluctuation, the frequency changes. And then frequency changes, then you have the band broadened. So if you carefully analyze the band shape, you can get information on this kind of polarization, which we call solvent-induced dynamic polarization of the molecule. Okay, so I repeat that we often say that carbon is delta plus and delta minus, but delta plus and delta minus is not constant for all the time. It changes with time. It changes, maybe very rapidly within picosecond or time scale. It's fluctuating. So dynamic polarization molecule. So this is a new concept we introduced to explain the Steven results. So I now come back to this one. So this is actually the picture showing the same thing. So that's solvent-induced dynamic polarization, and the dipole moment fluctuates like that in a very short time scale in picosecond. And that causes the width of your vibrational band. Solvent-induced dynamic polarization. Okay, this is the same thing. And we used this concept to explain the relationship between the peak position and bandwidth we found for steel beam. And what we think here is that you have the double bond in the S1 state. But we think that the double bond occasionally is polarized into single bond like that. But very quickly comes back. So here I plot the frequency like that. So most of the time, the molecule is in this double bond state. But if the solvent comes closer and it favors the polarized structure, then it goes into this polarized state. And then the frequency comes down to the single bond frequency. But if the solvent goes away, then it comes back to double bond. So the most of the time double bond, but occasionally going into single bond, but come back very soon to the double bond. This is a simple model. It corresponds to the fluctuation of dipole moment I showed. So solvent causes this kind of dynamic changes of the structure. Because a solvent produces very, very strong electric field, under this kind of electric field, this structure can be more stable than this structure for short time. So the model is like that. Then if we have this kind of change of frequencies, what kind of band shape and peak position we have? And we formulated the band shape and peak position when we have this kind of dynamics, which called the exchange dynamics. And then we found that if we have no exchange, we have the band here, omega 1. But if we have exchange like that, then the band changes like that. It goes closer to omega 2 because it occasionally goes to omega 2. So it effectively, its frequency, peak position goes to lower wave number. And at the same time, the width increases. Okay? So if there is no exchange, it always stays like that, then it is the omega 1 wave number with very thin or very small width. But if you have this exchange, the peak position is lowered closer to omega 2, and the bandwidth increases. And if we formulate this one, I'm not going into the details, but I published a paper in 1997 about this kind of exchange model for bidirectional dephasing. and found out this is a peak shift, and this is a bandwidth increase, that there is a linear relationship between the increase of the or decrease of the wave number and the increase of the bandwidth. And tau is a constant which represents the phase shift during one hop to omega 1 to omega 2. But I'm not going into detail. But anyway, it's constant. So using this relationship, we interpreted the result that I showed here. And from here, we know that the slope of this straight line we unexpectedly obtained is equal to tau, the ratio here. So we can determine tau. And then tau is equal to 1.4. And then if we do use that value, we can convert this peak position to peak shift. And eventually, using this tau equal 1.4, we can convert this peak shift to W1 here. Actually, W1 is a rate for a double bond polarized into a single bond. So how many times it occurs, like that. So by using this model, we are very nicely able to fit the observed band shape with this model, exchange model. So here I show you the observed spectrum with a full line in hexane. And here we have the same observed spectrum in full line in dodecane. So you certainly see there is a peak shift, from here to there, and the bandwidth changes. But these changes are very nicely reproduced with the dotted line, which are theoretically obtained from the model. Okay? So the model very nicely explains why the band shape changes depending on where the solvent, what the solvents are. Okay? So by doing this fit, we are able to tell that W1 in hexane is, in hexane, W1 is 2.7 to 10 to the 12th second minus 1. That means in every 370 femtoseconds, it goes into double bond, single bond, but come back very soon. But in dodecane, it goes into a single bond only in every 70 femtosecond. So the rate of polarization is almost doubled in hexane than in dodecane. This is because the solvent fluctuation is much faster in hexane than in dodecane. It should be related with the viscosity that I mentioned. If the solvent is very viscous, then the solvent fluctuation is slow. Then that makes this fluctuation slower. That is our understanding. And we now know that the rate of polarization, dynamic polarization, is much larger in hexane and dodecane. And isomerization rate is 70 picosecond in hexane and 120 picosecond in dodecane. So we think that this isomerization rate is related with this polarization process. And then it is reasonable to think that once the double bond is polarized into single bond, it can rotate. So if this polarization occurs, and if the bond stays in a single bond condition for a long time enough, then it rotates. But it mostly comes back. Okay? So apparently, by looking at by Raman spectroscopy, it's double bond. but for some time it polarizes into single bond, and then reaction can occur. This is what we think about the mechanism of isomerization. So this is a conclusion from here. So still being in the excited state, it seems that it's a double bond here. But it can polarize into a single bond like that, and then it can go to isomerization if it stays here for a long time. But mostly it comes back, so no reaction. And if we do Raman spectroscopy, then we observe the double bond frequency, but in hexane there are more chances for going into the single bond, so the frequency is observed lower. And if you measure it in dodecane, it does not go into the single bond so often. Then the frequency stays higher, and the bandwidth is smaller. Okay? So by analyzing the bandwidth or the band shape, we are able to discuss the dynamics of S1 transthromboane in this way. And this is called the dynamic polarization model of isomerization, and we published many papers from that. But I must tell you, this is still a hypothesis. So it's not written in the textbook yet. So I'm not sure whether how many people do really understand and agree with this model, but probably in 50 years' time, you all know that it is really true or not. I believe it is true, but I'm not sure whether you really understand and agree. And so I'm asking you to prove that whether this is true or not, because you will be still alive after 50 years? Probably. Okay, so science is that kind of long-term thing. If we want to say something very new, it's not easy for other people to accept new things. So although I am really convinced of this model, but most people do not understand what I'm saying. But I try to tell you, and hopefully you understand. But I think this is not bad to think that it's a very dynamic system. It's not always a double bond, but it can change, according to the fluctuation of solvent. Okay, this is the story about time-resolved Raman spectroscopy, and this lecture is until 9:20. So I use the remaining 20 minutes to talk quite different thing. Okay, maybe we have more time to stop. So I spent maybe 20 years for doing ultra-fast time-resolved Raman spectroscopy, and around 2000 I felt that I have understood how the reaction proceeds by this model. So I switched my research to something different, and actually this was helped by Taiwanese students of mine, and a student named Yu-san Huang came to my laboratory in the year 2000, and she graduated from the agricultural chemistry department of NTU, and her father got the degree from the University of Tokyo, and so he wanted his daughter to do the same thing, and so Yu-san wanted to do the graduate study in the University of Tokyo, and somehow she came to my laboratory, and she was interested in Raman spectroscopy, but her background was biochemistry. So she asked me, is there anything that we can do by Raman spectroscopy about biological related subject? And after some discussion, we decided to start looking at living cells by Raman spectroscopy. And that was really a new thing, Not many people were doing that. So after that, we spent many times and a lot of money and a lot of people in doing Raman spectroscopy of living cells. So I can tell you that I came up this ladder starting from the molecule in the very ultra-fast regime, very small world, to the real world of biology or organelle cell by using time and space-resolved Raman spectroscopy. I talked about time-resolved Raman spectroscopy here, but if you go to a larger scale, it is also very important to space-resolve the information. So in a cell, you have many organelles, so the Raman spectrum changes where you measure. Okay, so you have to space resolve your Raman measurement. So it's called time and space resolved Raman spectroscopy. So we want to space resolve organella from one cell. But the time resolution, can be much slower because the change in the cell is much slower than, in the picosecond or femtosecond. And there is one famous guy called Erwin Schrödinger. I'm sure you all know about the Schrödinger equation. But he was also interested in biology. And in a book he wrote in 1943 called What is Life? And he said, how can the events in space and time which take place within the spatial boundary of living organism be accounted for by physics and chemistry? So he said, for the thorough, deep understanding of life, we need physics and chemistry, and the information should be space and time resolved. So what can we do with time and space resolved measurement and physics and chemistry? My answer is to do time resolved Raman spectroscopy, space and time resolved Raman spectroscopy of living cells. So the question here is, what is life at the molecular level? So biological people do a lot of researches, but they probably discuss a lot about, say, gene presentation or something like that, but they are not really interested in what is life. And so then, can we measure and quantify life? It's a very big question. So you say that this cell is living, but this cell is dead. Can you make distinction between living cell and dead cell by Raman spectroscopy? And we challenged that kind of thing. So this is apparatus that I just briefly showed in the picture, but this is another system. So we have the microscope here, the microscope objective, and you have the laser, and the laser coming in to the sample through an objective lens. And then here you have the sample like this. And then you shine the laser, and the scattered light is collected by the same objective lens backward, and then go here and go through this filter and go into the spectrometer. In the Raman spectroscopy, the important thing is that we can do it non-destructively, so we can see the living cell as it is. And less invasive, we shine the laser, but its effect is very small. And label-free, we can measure it as it is. For example, in the fluorescence microspectroscopy, you have to dye the molecule, or you have to gene manipulation. And we have the nice spatial resolution of this kind, and we can measure it in a relatively short time, maybe 10 seconds or 1 second. Then, if you have this kind of apparatus, you can make a very nice imaging picture of, say, in this kind of living cell. This is a microscope picture, and here you have the distribution of lipid. So lipid is distributed like that in this particular cell. And if you look at protein, you have the distribution like that. And if you see the carotenoid in the living cell, it has this kind of distribution. So this kind of molecular mapping now you can do by Raman microspectroscopy. And yeah, that clock is 10 minutes fast. So I still have 20 minutes. Very good. So we actually constructed many advanced systems of Raman microspectrometer, but I skip these stories in detail. That's too much specialized. But I can tell you that nowadays we can get this kind of molecular imaging in 5 seconds. So if you have the Raman spectrometer and you have a sample cell, and you can make this kind of image in 5 seconds. It's a relatively short time. And we are now trying to shorten this measurement time. And as I said, the commercially available system is not good. If you use just a commercial system, it will take maybe 10 minutes or something. So here that I repeat what is life at a molecular level. Can we measure and quantify life? So the first living cell that we studied was fission yeast, Saccharomyces pombe. Why we selected this? This is the simplest eukaryote that is familiar to our life. So we use yeast for making bread, making beer. Actually, this particular species comes from the beer brewed in Africa. And this is actually safe and easy to handle. We are physical chemists, and we have no special knowledge about microorganisms, but we can still handle yeast quite easily. And model for higher organisms, because it goes this kind of cell division. Cell division is a very fundamental process of living things, and we can look into that process by looking at cell dividing. Okay, so this is a fission yeast that we selected. Yusan and I selected for a study, and here I show you some image with GFP. You know GFP, green fluorescent protein, which labels, say in this case, mitochondria. And if you shine a laser, you can see the image of mitochondria like this. This method is very, very extensively used in biology. And a few years ago, a Japanese professor called Shimomura got Nobel Prize for finding GFP. Some of you remember. But it took 40 years for Professor Shimomura to get Nobel Prize after his discovery of GFP. But as I said, in Raman, it's only 2 years. So you can see, say, mitochondria by labeling it by GFP like this. But Raman can do it without doing that. And here the whole cycle typically takes 3 hours. And if we can measure, say, a spectrum is 1 second, we can time resolve the process, And also the cell size is this is micrometer, 10 micrometer, 2 micrometer. And we have the 0.3 micrometer spatial resolution. We can space resolve those organella. So this is the first results which we obtained about 10 years ago. So Yusan is here. And in this experiment, we have yeast under microscope, and we fix our laser beam here and waiting for the cell to divide. So at 0 minutes, we have this spectrum, which can be interpreted as protein. The SN ratio is not very large because at the time we just started the experiment. And after 11 minutes, this nucleus is split into two like that. And if we shine the laser here, fixed, then we have this spectrum. The spectrum changes drastically because the molecules existing here are different from 0 minutes and 11 minutes. And if you go to 31 minutes here, you also have this very strong Raman bands. And after 45 minutes, you barely see a septum is formed here. And then the spectrum changes very much. And then the septum is matured at 62 minutes. And after 72 minutes, the cell divides into two. And then you have the cell wall here. And here you have the Raman spectrum of the cell wall. This is a real time and space resolved Raman spectra of a living or dividing fission yeast. And until that time, there are few or more than few papers reporting the spectroscopy of living cells. But there is no way of convincing that the cell is really living. Okay? You cannot tell whether a cell is living or not by just looking at by microscope. But in this experiment, the cell divides. That means it's living. So it's a really living cell that's measured in this experiment. And I think this is a real first example that Raman spectroscopy was used for looking at living cells. So first, we were very much interested in these strong Raman features, and we discussed this one. So this is a spectrum. It's much better than showed, higher SN ratio. And this red spectrum is obtained from the east. And the blue one is a Raman spectrum of phosphatidylcholine, which is a lipid, phospholipid molecule. And you see many bands in the east are also existing phosphatidylcholine. So that means the red spectrum contains a lot of lipids. Okay? And all the other small peaks can be assigned like that, shown here. But there is only one band here, 1602, which is not ascribed to the lipid. So what is this one? We still do not know, okay, clearly. But we did many things about this one. So the 1602 wave number band here seems to reflect cell metabolic activity that we found. Firstly, if we do the mapping, then this is a microscope image. This is a mitochondrial image obtained by GFP labeling. So this is a 1602 distribution, and this is a lipid, 1446, the lipid Raman band. So it seems that the 1602 wave number band arises from mitochondria because the distribution is very similar. So we first thought that this band comes from mitochondria. And then we found an interesting thing. If you have yeast here, here, and then if you add some nutrients, food to the yeast, then this band increases. Okay, you see? This band increases. So if you take the difference, you get this one, and all the other bands did not change, but this one only increased. So addition of nutrients increases intensity. So if the yeast cell becomes active, then this band becomes stronger, that we thought. And in reversely, if you add KCN to the cell, then this band decreased. Other bands stayed constant, but this one only decreased. Yusan first found this phenomenon that's really interesting. So I suggested Yu-san to do the experiment. What happens if you add KCN to your sample? Yu-san first declined to the experiment because she did not want to kill yeast. But this is a scientific experiment, so eventually she did the experiment and found that KCN decreased the intensity. So we thought that this band might reflect the live activity of the cell and might be the Raman spectroscopic signature of life. So if you have this band, yeast is living. If this band decreases or disappears, it dies. But this is a really attractive idea, but we have to check it very, very carefully, as I'm going to tell. Anyway, this is a very interesting band. So I show you another example. It's another kind of yeast. It's called budding yeast, cerevisiae, and it is well known that a black particle appears in a vacuole. You know, vacuole? Vacuole is an organ in a cell in which there are many unusable molecules are stored. And it's a big one. This is vacuole. And a black body appears in vacuole. It's called dancing body because it moves dancing around in the vacuole. And we know by Raman spectroscopy that the main component is the polyphosphate. And I was collaborating with Suntory company, you know Suntory company, at brewing beer and whiskey, and they know they have the experiences with dancing body. If the dancing body appears, the cell activity is lowered. Then they stop fermentation. Okay, so the appearance of dancing body means the decreasing of the living activity of the cell. So this is a time-lapse experiment under microscope. So the same budding yeast. So 0 minutes, you have no this vacuole, no dancing body, but the dancing body appears, you know, very suddenly at 6 hours, and then dancing around, and actually it stops here at 8 hours, 15 minutes, and then the vacuole is lost. You have no vacuole here, and then the structure, you know, destroyed. So the cell is going to die. We trace this change also by doing Raman mapping. So here I show the same thing, and at first we have normal cell, dancing body appears, dancing body stops at 8 this time, and vacuole lost this time, and structure lost. But it is not easy for you to say that this one is living or not, dead. Okay? So if you do Raman for this one, the normal one, you have these distribution of phospholipid and polyphosphate and phenylalanine coming from proteins. Then we have the 1602 wave number band very strongly like that. So these are normal distribution Raman images. But after dancing body appears, you see the 1602 wave number band suddenly disappears as the dancing body appears. And then after that, there is not much change here, but the 1602 wave number band really disappearing, but the same thing. And then if you go to here, you see also by Raman you have, so here you have the vacuole clearly, but not here, and the structure is destroyed. And usually in biology, we detect the cell death by adding some dyes. If that dye penetrates into the cell because of the lowering of the function of the cell wall, then we decide it is dead. But if you do that dyeing, then these cells are thought to be alive, living, because there is still a cell wall there, and that hinders the penetration of the dyes. Okay? So when the cell is alive and when the cell is dead. So we thought that by looking at 1602, we can say that here the cell is still alive, but without this band, it is dead. So if this is true, you can tell the very early stage of the cell death by using the 1602 wave number band. This was what we are doing 5 years ago. So we are really excited to find this one. But it's not so simple. By the way, it is really interesting. If you give some nutrients at this point, then it comes back. Then you have the 1602 wave number band recovered, and dancing body disappears. So here, it's a reverse process. But if you go here, it's not a reverse process. So in a living cell level, you have some state between living state and dying state somehow. We never have that in the body, but it can happen in the cell level. And later, we developed a system using nonlinear Raman spectroscopy. It is called CAS. I'm not going into the details of this technique. And we were able to make this kind of movie of the cell. Here I show you that this is 1602, still here, disappears, and then this one, this is dancing body actually. So we can time resolve the process by very fast CAS method. Repeat here, that's still 1602, and then disappears and appears, and then the cell structure is destroyed. The process that I showed you is reflected in this movie. And we now are convinced that dancing body appears after 1602 disappears. So it's certainly related. So 1602 is somehow related with the living activity of the cell. But why? And very recently we found that this 1602 wave number band comes from ergosterol. It's a sterol molecule like that. And it is not known that ergosterol plays a key role in maintaining life. It is something like cholesterol in the animal cells, and it regulates the hardness of the membrane. But no one knows what the real function of ergosterol. But we found that ergosterol is a good marker of the cell activity. So how ergosterol can be the signature of life? So this is a question we are having right now. We have to solve it. One possibility is here. We do many more experiments of mitochondria with different types of mitochondria. And here we have the cell growth curve. It's called growth curve. We started cultivation here. At first we have what's called lag phase. And then it steeply increases at log phase and then stationary phase. And we found that mitochondria morphology, this is GFP image, are different in the lag phase and log phase like this. In the lag phase, it's a dot-like structure like this. But in the log phase, it's a string-like. So it can be different. And actually, Raman spectra shows that they are different. If you do in the lag phase, you get this spectrum that is quite different from that I showed. These spectra are definitely from proteins. So at this stage, dot-like mitochondria contains only proteins, no lipids. But if you go to this log phase, a string-like mitochondria, we see this strong feature that we discussed. So we first thought that these bands are from mitochondria, but it may not be from mitochondria itself, but lipid associated to mitochondria. because in the lag phase there is no lipids, okay? But still there are mitochondria. So mitochondria changes very much in the lag phase and log phase. But we are mostly discussing mitochondria in the log phase, where the cell is dividing very, very actively. Okay? So we found that this 1602 is associated with mitochondria in the log phase when division occurs very frequently. And we even found that if you see the mitochondria in this stage and fix the laser here and wait for this time, then the spectrum changes the proteins to the lipid. So there is a very rapid change of the nature of mitochondria without lipids to a lot of rich lipid. So when mitochondria is functioning, it needs probably needs a lipid like that. So we now think that the signature of life, 1602, probably appears only when mitochondria is active, only when mitochondria needs lipids to make energies. This is again a working hypothesis. We have to prove that. But at least 1602 can reflect some part of the living activity of the cell. And then we also found this is a time-dependent change of 1602 wave number band, and it fluctuates like that. This is the 100 second, so every 1 second it fluctuates like that. Okay? And so this is probably very similar to what I discussed, dynamic polarization. So chemical reaction proceeds because of the fluctuation. Okay? Also here, some living activity fluctuates like that. Mitochondrial activity fluctuates very, very rapidly. So I think one key thing in nature is a fluctuation. And I come to this one. Probably this is Chinese, and everything is changing. And Japanese people are especially fond of this kind of concept. You know, nothing can last forever, always fluctuating. And very fundamental physics, for example, elementary particles. The elementary particles are generated by the fluctuation. So if there is no fluctuation, nothing happens. Okay? So it is interesting to see everything in time and space resolved. So dynamic aspects of things we want to see to understand the real, deep part of nature. So I think I stop here and saying that Raman can do many things, starting from the photochemical reaction in the excited state, the picosecond, femtosecond, and it can also study those very fast dynamics in the living cell. Hopefully we can elucidate more deeply what life is at the molecular level. But also Raman can be used to, say, food science or medicine or many practical applications. So I hope by this lecture you will get interested in Raman spectroscopy, and if you are interested, please start learning Raman spectroscopy, and you all are welcome to visit my office at room 345 to discuss how you can use Raman spectroscopy. Okay, I stop here, and thank you very much for your attention.